Next, we're going to talk about the limit comparison test, which is another tool to compare two different series. So let's say that we have two sequences, a sub n and b sub n, and again, they're both positive. Now what we can do is we can compare the two series by taking the limit of the sequence ratio and checking what that is. And as long as that's some constant c that's between 0 and infinity, so in other words, a finite number like 7 or 2 million or anything that's a finite number, then both of the series have to do the same thing. And so they both either converge or they both diverge. Turns out that if c is 0 or c is infinity, then sometimes you can say something about the relationship between the two, but I'm not going to worry about that for now. We're just going to dive into a couple examples. And so first, let's look at this example here where we have this big mess in the numerator and then another big mess in the denominator. And the question is, how can we determine whether or not this converges or diverges when there's so much junk going on? And the real benefit of the limit comparison test is that what it allows us to do is just pull out leading terms. And so in the numerator, the 16n to the fourth is much bigger than any other term, just because it has the biggest power. The same thing is true for this n to the eighth. And so we might predict that this is going to be the same behavior as 16n to the fourth over n to the eighth. In order to show that that's definitely true, we're going to have to take the limit of the ratio of the original series and the one that I am comparing it to. And so I'm going to take this limit as n goes to infinity of all of the stuff that I had originally, 16n to the fourth plus 8n to the 1.5 minus 23n divided by n to the eighth minus pi. It's very annoying to write. And then I'm going to divide all of this by what I think it's probably like, which is 16n to the fourth over n to the eighth. And so now I need to figure out what this limit is. And at this point, you might be thinking that it looks horrifying, but it turns out it's not that bad because I can rewrite things. And so we know that if we have a compound fraction, then really that would be the same as taking the denominator and flipping it and writing it in the numerator instead. And so, in other words, I can rewrite this so that it's 16n to the fourth plus 8n to the 1.5 minus 23n divided by 16n to the fourth times n to the eighth divided by n to the eighth minus pi. And so now there's a couple ways to proceed. You could use L'Hopital's rule a bunch of times, or you could divide by the leading terms in the numerator and the denominator for both the first fraction and the second fraction. Or we can just make a note of the fact that the leading terms here and here both match. And so this limit is going to be 1 by comparing leading terms. And so I'll use LT for short for the leading terms. And so that means that by the limit comparison test, this does have the original series has the same behavior as what I just compared it to, which is the 16n to the fourth over n to the eighth, which I could rewrite by pulling out the 16 as 16 times 1 over n to the fourth, and that converges by the p-test. And so my overall answer for this example then is that it converges. Okay, now let's look at another example. And so here we have the sum from 1 to infinity of 1 over root n to the 1.5 plus 4. And so again, the idea overall is that this n to the 1.5 is going to be bigger than any other term in the denominator. And so chances are I can just drop all of the other terms and the behavior of the series is not going to change. And so what I want to compare this to is 1 over the square root of n to the 1.5. I just want to drop that plus 4 because it probably doesn't make a difference. And so again, in order to do that, I'm going to take the limit of the ratio of the original, which is the square root of n to the 1.5 plus 4, divided by this new thing. And so now, again, I have the compound fractions, and so I can rewrite it as the square root of n to the 1.5 over the square root of n to the 1.5 plus 4. And now this time, just to see how this works, I am going to divide by the leading term in the numerator. And so in other words, I'm going to multiply the top and the bottom by 1 over the square root of n to the 1.5. And so overall, I'm just multiplying by 1. And so when I do that, the top becomes a 1. And the bottom, when I combine these by putting this underneath here, underneath the root, then I end up getting the square root of 1 plus 4 over n to the 1.5. And so at this point, you can see pretty clearly, again, that this limit is equal to 1. And so by the limit comparison test again, the original series does the same as this new series that I compared it to, which is 1 over the square root of n to the 1.5. And so now, in order to figure out what this does, I'm going to want to rewrite this so that it looks a little nicer. And so this is really an n to the 1.5 raised to the 1/2. And so in other words, I can rewrite this as the sum of 1 over n to the 1.5 divided by 2, or in other words, 0.75. And so this diverges by the p-test, since p is less than 1. And so that means that the original, sort of backtracking through my logic, the original one had to diverge as well. Okay, let's look at this last example here. And so at this point, hopefully you can see that the power of the limit comparison test is to get rid of all the garbage that doesn't matter and to only focus on the stuff that does. Or in other words, it allows you to reduce to the leading terms in a fraction. And so for this series right here, where we have n plus 3 to the n over 4 to the n plus n to the 4th, I really need to know which functions are bigger than which other ones. And you might remember that exponentials are always going to be bigger than polynomials. And so that means that the 3 to the n and the 4 to the n are much bigger than the corresponding other terms. And so we might predict that this is going to be like 3 over 4 to the n. And so in order to justify that rigorously, again, we need to take this limit as n goes to infinity of n plus 3 to the n over 4 to the n plus n to the 4th. And then I want to divide by my 3 to the n over 4 to the n. But at this point, hopefully we can be more comfortable with the fact that that's just the same as multiplying by the reciprocal. And so now I can clean this up a bit. This will be the limit as n goes to infinity of, and now I want to compare sort of this numerator of the left to the denominator on the right. And so if I simplify that, it's going to be an n over 3 to the n plus 1. And then if I compare the numerator on the right to the denominator on the left, I'm going to end up with a 1 plus n to the 4th over 4 to the n. Okay, so now I have to keep track of what each one of these does. And so really I have some mini limit problems that I would have to do here in the numerator and here in the denominator as well. And if I were showing all of my work, then maybe you'd want to use L'Hopital's rule to verify that both of these limits are going to be 0. But for here, I'm just going to take that as granted, and this limit will end up being 1. And so again, 1 is a constant value between 0 and infinity. And so by the limit comparison test, my original series is like this new one. And so the one I compared it to again was 3 over 4 to the n, and that one converges. And in this case, it's because it's geometric with r equals 3/4, which is less than 1. And so backtracking again through my logic, that means that the final, or the original series also converges.